Live. So, tonight we're going to be talking about software complexity, which is a bit of a theoretical lecture, and then we'll finish up with some Git, fixing up history, which is certainly useful. It's not really like, it's kind of a bonus lecture. It's not something that we explicitly, I guess, assess in the course. It's more just like a useful tidbit for you all. But this is our last kind of lecture to do with design. Kind of one of our last kind of proper formal lectures, actually. This is probably the last lecture we do in the course that has accessible content. So we're really getting close to the end here. Very short lecture, don't worry. You'll be back into doing whatever you're doing normally soon. So the reason we're talking about this is because software is sometimes really simple. Software is sometimes really complex. We know that. And we need to have the ability to have conversations about it, right? Like if you can't find a way to express yourself about something, it's very hard to ever get anything done. So we need to be able to have those conversations. We're going to talk about two types of complexity, and we're going to talk about how to measure complexity, both kind of broadly speaking and then a bit more specifically. Fairly straightforward. So firstly, what is software complexity? Does someone in the chat, if someone said to you, describe what complex software is, not an example of it, but like actually define it, what would you define it as? I'd love to hear what your best guesses would be on this one. Time complexity? Yeah, okay. That's quite interesting. Time complexity is a certain way of describing software complexity. You sound like you're a 2521 student or a prior 2521 student, one or the other. What else? Brendan says time complexity. What else have people got? Nothing. Space? Okay. Space complexity, I'm sure you mean. Ethan says software that isn't simple in nature. That's true. Calling complex software that isn't simple is like saying that, your hard rock is something that isn't soft, which is kind of one way to describe it. Jeremy says complex software that takes into account as many edge cases as possible. That's interesting. I'd call that a causative, not correlative, not causative thing, as in terms of like, complex software can certainly not take in as many edge cases as possible, but quite often software that does take in many edge cases can tend to be a bit more complex. Yep. Alex says software with lots of different systems interacting. Yes, that's true. Generally, software with many systems interacting is complex. It's one aspect of complexity. Just like how, you can be a complex person because you have a bad relationship with your parent or something, and there are many other ways to be complex, but that's one way of being complex, right? So all kind of true. Brendan and George, in terms of time and space complexity, I think they're very reasonable guesses as to what we're talking about, though we aren't actually talking about that, because time and space complexity is an idea in terms of the performance of software. Measuring the complexity of how it performs is like a big data structures and algorithms topic. But what we're really talking about is kind of understandability, or the degree to which software kind of stumbles over itself. So, confusing and messy might be like two really friendly ways of describing what we're talking about with complex software. Generally speaking, complex software is divided up, like one way we can describe software complexity is dividing it into two different categories. So we said that, complex software is, something that's confusing or messy or many pieces, spaghetti. It's the opposite of simple, clean, elegant, easy to understand, very modular. We kind of had this design lecture, weeks ago where we talked about what makes good software, what makes maintainable software. And again, to some extent, complex software in some ways is the opposite of that, though not always. And this kind of gets to the point, which is that there are two types of software complexity that we talk about. The first one being essential complexity and the second one being accidental complexity. So essential complexity is complexity that's inherent to the problem. For example, if a user or client requires a program to do 30 different things, then those 30 things are essential, right? Like, if someone came to you and said, wow, your major project is very complex. You have channels and users and messages and reacts and pins and password resets. It's like, yeah, but that complexity is kind of essential because it's core to the application itself. It's not complexity that you can remove, right? So if it's complexity that's just not possible to remove, then it's what we would consider to be some essential complexity. Whereas complexity that is not inherent to the problem, complexity that essentially you add on top of it, is what we would call accidental complexity. And basically this is like things that are made more complex because you aren't doing good at your job kind of thing, right? Which we all do every day. For example, accidental complexity within like the 1531 project could be something like writing your own JSON decoder and encoder, or generating your own user ID, your own like session ID or user ID, instead of using a library to do that kind of stuff, because it's adding things to understand to your software, things that are potentially confusing, but they aren't necessary, and it was avoidable by some other method. As I said, essential complexity fundamentally can't be removed, but it can be managed with good software design, which is what we talked about in earlier weeks. So sometimes software like your project is just complex inherently, and you can do things to make your code easy to work with, but accidental complexity can be typically mitigated through engineering decisions, examples being smart use of libraries or a particular algorithm or approach that's a little bit simpler. There are easy ways to solve problems and hard ways to solve problems. Some of you might be a little bit young in terms of your programming journey, but when I go to solve a problem, a good example is how how I originally tried to solve your group allocation for the project. I used to kind of, I'd make like I'm not going into this in much depth because I didn't plan to. Oh, my eyes. But typically you'd have, I used to do something like, classes, and then I'd say, M15A or something. And then that class would have like, 5 groups, and each group would have students. So, the whole data structure would kind of look like this. And the original kind of thing I wrote a couple years ago, it used to, I guess, like run through all the students and start like allocating them to different groups and stuff. And that it was super complicated, and I had all these edge cases and all these, hacks on hacks on hacks. I mean, typically software like this, you don't feel like you need to maintain, because like as a lecturer, I'm maybe going to use this once or twice and something like that. So all the course changes, so there's no need to perfect it. But it's very ugly. It was a very complex piece of software, and most of the complexity was accidentally complex. Whereas what I ended up doing this year was less complex, because I just made a different decision about the design or the approach of the software, which was that essentially we went and got imagine everyone's like a student. We got every single student like this, and they were all essentially in their own array, or array by themselves. And then what we did was we would look at preferences, and we would say, okay, D and E want to be together, and we would basically just start merging these groups. So essentially, if you start with a bunch of groups that are all just one person, so you've got 600 students, you've got 600 groups, you're now on a mission to just keep jamming groups together until you end up with the right amount. So D and E would be together, and if A and B preferenced each other, you do this, and you just kind of keep doing that. We did this kind of stuff where we'd layer this in, and we'd join people based on their preferences. So once we'd done all the group preferences, we started combining people based on hobbies and if they had preferences around, gender and whatnot in their group. And, eventually you just kind of end up where you would slowly be merging things together, and then you'd merge this group with that group, and then this with that, and this with that, and, you'd end up in situations like this. Well, you didn't. It was written in a way that you wouldn't end up with stuff like this. But point is, actually, there's a lot of students who don't preference anything, and they're the best, because you actually get to a point like this, but then you have a whole bunch of students at the end here that didn't preference anything, and they're really easy, because you basically then at the end, once you've like formed all the macro groups, you can just come along and like kind of drop the rest in, so to speak, like this. So that was very easy. But the point is that that software was easier the second time to read and understand, even though it did the exact same thing, just a different way, because there was less accidental complexity there. There is a certain amount of fundamental complexity in just group allocation, and I'm sure that was not the best way to do it. I'm sure I missed something. And there's probably algorithms if I would have Googled stuff, but a lot of accidental complexity avoided on the next time. Is there a concrete process for distinguishing accidental and essential complexity? These are really interesting questions. To an extent, yes, but again, most of them are correlative, not causative. It's very hard to fundamentally go, hey, this piece of software is complex, and it is accidentally complex. There are definitely ways to look at the complexity of software. You can look at the number of files, or how those files are interconnected, or how big functions are. Like, there's a lot of kind of these leading indicators that you can look at, but they don't always tell you what is essentially complex and accidentally complex, which comes again back to like why you should be excited to be doing tertiary education for computer science instead of learning it online through some kind of free course, because you'll come out being able to program the same as all these other people learning for free online, but hopefully you come out being someone who can better identify well-written software, who can write more maintainable software, who can distinguish between accidental and essential complexity a bit better. So a few fun questions there. How do we measure software complexity though? We kind of understand what it is. We've talked about you can kind of measure it. We haven't said that you can necessarily measure or distinguish between accidental and essential complexity, but we can still try and measure it broadly. So there are three ways we're going to look at. The first one is to look at the degree to which the software is coupled. We're going to look at the degree to which software is cohesive, and then we're going to look at the cyclomatic complexity of our software as well. So firstly, in terms of coupling. So when it comes to software coupling is simply a measure of how closely connected different software components are. And what that means is that when you look at a series of components in software, you want to make sure that... I'm just reading ahead, sorry. Let me read ahead a slide. Yeah, so what you want to make sure generally in software is that if you have lots of different pieces of software, that they are separated out as much as possible. So essentially, you think about if you have a file and then that file imports 3 other files, that file is now linked to 3 other files, right? But if that file imports another 10 files and all those other 10 files import each other, it's kind of like a web. So when you think about coupling, think about a web, like a spider's web. If you just have like lots of little things all interacting and all connected together, I mean, I don't know. I think I saw this on Discord or something in the 2521 lecture. Someone was making a joke, but you got that like what was complete paths or something? Diagram. Oh my god, I can't remember. It's been like a year. Diagram. Spell. This is kind of complex. This is what you would call like tightly coupled software. Everything's really well connected to each other. So it's a measure of how closely connected different software components are. When you think about a software component, this means a different thing in different languages. But in something like JavaScript, you could think about it like a file. Your auth file, your other file, your channels file, or you could think about it like functions potentially too. There's a bunch of different ways you could think about it. There's no universal way to think about it, but it really is just the measure, are things loosely coupled, really well separated, or are they tightly coupled, super integrated? For example, a web application tends to have a front end that is loosely coupled from the back end. And you know this because in the project, you've been writing an interface that means that your front end can be loosely coupled from the back end. So loose coupling is good as pretty much a general rule. It's really good when your software is not kind of all connected together. And the simple reason for that is that it makes your software more resistant to change, back to maintainability. You should already be at least half familiar with that idea. Cohesion on the other end, though, is the degree to which elements of a module belong together. Now, these two ideas sound nearly similar, but what cohesion is talking about is like, whilst you want like think about it like this. You've got a bunch of auth functions, and you've got a bunch of channels functions. Auth and channels are different. So you want them to be loosely coupled, which means that you want to put them in different files, like you have. Whereas auth register and auth login are similar. You would say that they are cohesive together because they are similar. And therefore you want to keep them in the same place. You know, whether it's the same file or different files in the same folder, you want to keep these things together. So elements belong together if they're related. So like register and login, those things are related to each other, so they should be together. And therefore high cohesion is good. So think of it kind of like coupling is, you want little coupling, because that's like you want to say that things that aren't related to each other should be separated as much as possible. And cohesion is saying that things that are related to each other should be connected as much as possible. So that's kind of the two differences there. So when we ask you the question, you know, to what degree would you consider this software cohesive? That is saying, go look at it, and do things that are similar or connected seem like they are actually connected? And if we say, you know, is this software tightly or loosely coupled? Again, you'd look at it and you'd say, okay, for things that don't need to be together or aren't closely related, are they separated out? You know? Nope. Sorry, I was just looking at something. And now we got onto a kind of the last bit. No, yeah, last bit here, which is cyclomatic complexity. Now, cyclomatic complexity is a topic introduced by an old colleague of mine. It's a very interesting topic. I wasn't too familiar with it. They come from a programming languages background, which is quite interesting because they're able to think about software a bit more theoretically than myself. But cyclomatic complexity is essentially a measure of the branching complexity of functions. So what that means is that it's a way of saying, it's a way of trying to numerically assign a value that describes the complexity of a function to a function. So if you write a function in JavaScript, I should be able to look at it and be like, that's a 7. I'm going to give that a score of 7 for complexity. And what it does is it computes the number of linearly independent paths through a function. And what that means is, like, if we go like look up JavaScript function, we'll look at a few examples together soon, but let's just have a look at one here. Random piece of code from the internet. Have a look at this random piece of code here for a second, right? Here's a function, and like, let me ask you the question. How many linearly independent ways through the program are there? That means, like, how many different decisions, how many different states can exist that change my flow through the program? And if you're following along, the answer is 2. Because you're always going to have to go through that in name, right, part here. This is different JavaScript, by the way. But whether you go into the if or the else is really up to a certain value. So there's really like 2 scenarios. So think of it like, what are the 2 scenario flows through a function? So in this particular case, cyclomatic complexity is just kind of a flow complexity, or what you call a branch complexity, because every time you go into a while statement, a for statement, a switch statement, an if statement, an else statement, you're all dealing with what you call branching. Branching being the idea that, you know, you've kind of got one linear flow here, and when you hit those points, there's 2 different ways you can go. So it's kind of like a linear branch into you know, a branch off a linear flow into multiple flows. There's a formula we use to calculate the cyclomatic complexity, which is E minus n plus 2, where E is the number of edges and n is the number of nodes. Now, what the hell is that? Well, what we're going to do is we're actually going to take our code and we're going to represent it as a diagram, or what you'd call in discrete mathematics a graph, like this. So if you have a simple piece of code like the one we looked at with the screenshot, you'll see here that we have a function called foo that says, you know, if A, then do B, else do C. And if we were to try and draw the flow of this, because drawing's really easy, right? You'd simply write A up the top, then B, and then C, and then D. Well, these don't correlate to anything. Like, I know A is a function and stuff, but these don't even have to have text in them. They're essentially just points in the code. It's like telling all the different story possibilities. And what the cyclomatic complexity formula says is that if you do E minus n plus 2, how many edges do we have here? Well, we've got how many lines? 1, 2, 3, 4. So that's 4. How many nodes do we have? 1, 2, 3, 4. That's 4. So e minus n, 4 minus 4, plus 2 is equal to 2. So the cyclomatic complexity of that piece of code is 2. The higher the number, the more complex the code is, right? Very, very straightforward. Now, if we look at a second example here, we've got another piece of code, except it's got a nested if statement. And what we're going to do is we're going to try and write out that code, right, essentially, as like A, B, C, D, E. The E is not really necessary again, but I could kind of draw this out with very different letters, and maybe let me just show you this. So like what we might do over here, for instance, is say, well, I know that I'm going to have to start here with that if statement, but I'm either going to go into this part or I'm going to go into this part. You know, and I could annotate this any way I want. If I go into this part, that's the part where I call B. If I go into this part, that's the part where I call else. Okay, and once I'm in the else, what I'm going to do then is that I'm going to go and call another if statement. So maybe I'll draw another line here. I've got my next if statement for like C. And then from that if statement with C, what's going to happen is I go inside the if statement, or I don't go inside the if statement. And if I don't go inside the if statement, I kind of end the program. And if I do go inside the if statement, I call D. But, you know, maybe to make our lives easier, let's say that, you know, the end of the program is down here, like this, so that, you know, if I do C, I kind of end the program, and if I do D, then I end the program. And if I do B, once B's done, I also end the program. Now, the point I'm actually trying to make here is that I've drawn this diagram pretty higgledy-piggledy. You might be looking at it and being like, oh, okay, that's a bit weird. But the point is that as long as you actually draw your diagrams of your code out very logically and consistently, you'll actually get the exact same answer. So in this case here, what I've done is I've actually nearly drawn out every line of code. I've been like, well, up the top here we have our, like, you know, our if A. And then, you know, if you enter that, it's B, otherwise you go to the else. And then from else you have to go to the if, that's the only place you can go. Then from the if you can either come down here and finish the program, or you can come down to D and finish the program. And after B you can finish the program. And let's count these up. How many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8. We got 8 edges. How many nodes? 1, 2, 3, 4, 5, 6, 7 nodes plus 2 is equal to 3. What's the answer? 3. However, you'll have a look here on the slides. We have a different answer. On the slides we have 6 minus 5 plus 2. And this is because the diagram has been drawn differently here. Does that mean we got it wrong? No, not necessarily. What this probably means is the diagram being drawn here is slightly more succinct. What do you notice about our diagram? A couple things. Firstly, you'll notice that both B and D parts here go straight to the end, whereas with the if C parts, for some reason, instead of just going straight to the end, I put this other node here. So naturally we can just do that, like this. And then similarly, this else thing here doesn't achieve much because, like, you have to go through it, so we could also join that. And now we suddenly end up with a diagram that's similar to what's on the slides, where it would be 6 minus 5 or something like that. But here's the... Oh, wait, did I? Maybe 1, 2, 3, 4, 5... I don't think I... Oh, no, I did. That's okay. 6 minus 5. Yep. And here's the interesting thing, and this is why you shouldn't stress about drawing this diagram wrong. Most of the time, if you get a different result to someone else, if you have been drawing it correctly, it's because you added redundant linear flows. So that's what you notice about these two things I cut out. They weren't branches. They were kind of like pit stops on a single road. And therefore, whenever I remove this node, I also remove an edge, because instead of having one node with 2 edges, I now have no node with 1 edge. So redundant additions to the diagram essentially add 1 extra unnecessary node, which adds 1 extra unnecessary edge. And if you look at the math formula for it, E minus N. So you kind of just like, you can't draw it wrong. So don't be like, oh my God, should this be a thing? Should this be a thing? As long as you're actually describing the program logically, you'll actually end up with the same result, even though your E and N might be different. So the question that Alex has just asked too is, how does this deal with loops? Well, let's have a look at this function here, the foo function. And when you draw out loops, you can kind of, again, if it's a bit too heady, think about it like this. We have our starting point, you know, which is our foo. And then from there, what are we going to do? We're going to enter the while loop. Now, this is not how it's drawn necessarily on the slides, but I'm just trying to show you how much easier this can be. You enter the while loop, and when you enter the while loop, you kind of have two options, right? You can either A, go straight down here to C, because you skipped it, or you can enter the while loop and do B. And once you've done B, what do? Well, you have to come back up to the while loop. And then once both of these are done, you finish the program. Like this. So what do we got? How many nodes? 1, 2, 3. Is it nodes minus edge or edge minus nodes, right? Yeah. You know, 1, 2, 3, 4, 5, 6. 6 edges minus 1, 2, 3, 4, 5 nodes plus 2 equals 3. Oh, what have I done? 1, 2. What have we done? What have we done? Trying to blame this on you. Clearly I've got one node missing or too many edges. 1, 2, 3, 4, 5. 1, 2, 3, 5, 6. So naturally what's different to the diagram... Oh, okay, sorry, obviously. So what they don't have here, which I think I've screwed up, which actually makes sense. So this is actually me not doing it right, is that here, this point here is pointless because these are like the exact same 2 points. In terms of B here should actually go to C. There is no kind of last bit here because C is the end of the program, you know. So that's the main difference. Now, obviously, the diagram on the slides, and I'm just intentionally trying to draw these differently so you can kind of think about it different ways. Actually, you don't even need that. Sorry, my apologies. I'm being completely confusing. Let me just show you exactly what this should be and explain what's gone wrong. So I used to have this like this, but here's the problem. You actually never go from B to C because the nature of while loops is that you don't just like leave them randomly. It's not like an if statement where you go into it and then you execute stuff and then you leave. Obviously with a while loop, you come into the while loop, you execute the stuff, and when you get to the bottom of the block, you go back up to check the condition again. So that what I'd actually drawn was wrong, and that's what I mean. Like if you draw it wrong, if you don't actually represent code, you're just going to get the wrong answer. But here, it's drawn right now, because there's no way to go from B to the end or B to C. That's all dumb. That's just me being dumb. But when you go to B, you do actually go back to that while loop. And now we have 1, 2, 3, 4 nodes, and we have 1, 2, 3, 4 edges. So we get 4 minus 4 plus 2, which is equal to 2, as you'd expect here. Now, last two examples, this one here is a little bit more complicated. You can see the diagram on the right here. If we just kind of follow this for a second, this is your starting point. Now, obviously, you can, if you enter the while loop, you can just skip straight to the end. However, if, and maybe I will draw this out kind of just lightly because that diagram's a bit small. Let's say you start at the top. Okay. Now you can either enter the while loop here, or you can leave the while loop and go straight to the bottom. Easy. Once you are in the while loop, you kind of have two options, which is you either go to the if statement or the else statement, and inside that block, there's no other real alternative. Let me just write these out here. So we got while, we got if, and we got else. If you go into the else statement, once the else statement's done, you end up I don't think I should have labeled that correctly. Yep, one sec. Program starts, you come down here and you hit the while loop. What I did before was salvageable. I just think this might be a bit easier. You hit the while loop. From the while loop, you enter, right? And from there, you can either go to the if, or you can go to the else. These are all fine. I just, like, basically what I did wrong before was I labeled the while loop part wrong. I put the while here. But what I actually probably should have done is, like, you've got your end of program here. This is your if statement, and this is your else. Now, the point again is that this little thing in the middle here is not necessary. I just kind of drew it out intuitively because it's like, well, you enter the while statement, okay, and then you come along, and then from here you either go if or else. But obviously this is completely redundant. So you could get rid of it, but again, because getting rid of it would remove one node and one edge, so it doesn't really matter. If you get to the else statement, you naturally come all the way back to the while loop, right? If I start drawing some arrows here as things get a bit directional. If you go into the if statement, you now have another choice, which is either A, you go into the next if statement, or B, alternatively, you skip the if statement and you end up back here too. And in the next if statement, no matter what you do, you end up back here as well. Right, a little bit of poor lines, but that's okay. Just give you a bit more space. That's kind of where we ended up. Now the arrows I know are a little bit annoying. Probably should have done this kind of thing in Miro or something. But the point is that what's drawn here is exactly the same. It just kind of looks different. If we sum things up as well, how many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 edges. The number of nodes, 1, 2, 3, 4, 5, 6, 7. We have 7 nodes, 9 edges, 7 nodes. Plus 2 is 4. So we get 4 as well. Once again, we did draw more. What's redundant on this diagram? A couple of things. This is redundant at the start. You don't need to kind of go from the start of the program to the while loop since it's a linear flow. And also, in the case where you enter the if statement, but you go to the next if statement, this is also linear, because if you do go inside the if statement, there's no reason to kind of have a block there. You could just kind of get rid of it. So there's kind of just 2 lines from that, really, I think. Well, yeah, this is technically redundant here too, but that's okay. It really just depends how you want to draw it, but that's how you do a while loop example. Sorry for my poor drawing, and maybe let's just do one more that conveys the point. We'll pull this back up. So similar program here. Might make this smaller again just so you can see the rest of the code. So what we're going to do in this case, let's try and draw this one a bit more compact. We know that the program starts off, and we know that the program kind of starts off with a while loop, basically. And then we know from that while loop, similar to the other program, we can either come straight down to the end, or we can enter the while loop and go to the if statement, or we can go to the else statement. So we have the if up here, and then we have the else down here. Okay, and then from the if or else, you pretty much end up back at the exact same place at the start anyway. Hope we got that right. How many lines we got? 1, 2, 3, 4, 5. How many nodes we got? 3. Is it 4? Oh, no, I've done it wrong. Oh, what have I done wrong here? Okay, let's have a look. What do we got? So you always have to go into either the if or the else. Maybe let's draw it slightly differently. After both the if and the else, you kind of end up in this common point here, which is like this last year plus 1. And then from that year plus 1, you always end up back up here. Now in this particular case, now I've got 1, 2, 3, 4, 5, 6 lines and 4. No, oh, I had it right. I forgot to draw the circle down here. Okay, what I had before was fine. Let's go back to that. There was just a circle missing. I was very confused. I was like, I'm pretty sure this is right. There's just a circle down here, right? Because we've got 5 edges and 4 nodes. 5 edges, 4 nodes, plus 2 is 3. You notice the slides have drawn things slightly differently here. And in fact, the main difference with what the slides have drawn is that the slides essentially have 1, 2, 3, 4, 5, 6 nodes, whereas we only had 4. And that's because the slides actually contain a couple of irrelevant linear paths. For instance, this one here, right? As well as these 2 here that end up to this node, because it always goes back there. You could just draw these 2 lines straight to the end. Yeah, anyway, the point is, if you look at, there's a few kind of redundancies here, but the point is that doesn't make it worse. Yeah, Alex says, I guess you could say it has some accidental complexity. There are no points for it being shorter or simpler. Make sure it describes the code literally. And you know what? If you're not sure, literally you could draw it out with lines of code. Like you could quite honestly like start off and be like, well, you know what? Line 1. Can I draw with 2? Oh yeah, let's use paint to its full power. I've got like a line. One sec. Yeah. Okay, so it's like now I'm like, okay, I've got line 1. From line 1, I have to go to line 2. From line 2, I have to go to line 3. From line 3, I have to go to line 4. From line 4, though, I have to go to line 5. From line 5, I can either go to line 6 inside the else if, or I can go to line 7, which is the else, and then line 7's always going to take me to line 8. And then from line 8, I'm always going to go to line 9. And then from line 9, I'm always going to go to line 10. Right? And then from line 10, I'm always going to go to line 11. Then from line 11, I'm going to end up back on line 4. I guess. I'm worried I've done something wrong. Yeah, this is fine. And then before from line 6, when we go through line 6, if we go through the if, the next one we go to is line 9. So we come up to line 9. And what's missing here is if the while statement is false, we go from line 4 straight to line 12. And then line 12 goes to 13. And line 13 goes to 14. And let's add these up, right? How many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many nodes do we have? 14. Oh, that's good. Yeah, I was really worried. 14 plus 2 is 3. And I like showing this example because what it demonstrates to you is that this isn't some like all the little nodes and stuff I was drawing before are not some like really cognitive demanding thing. They're actually just summaries of this where you're like, we don't need to write out these 3. We can just treat that as a node. We can treat that as a node. We can treat that as a node. You know, that's all that was really happening. It was just a simplification of this. But, you know, if you're ever in doubt, you can just write it out like this. It's very hard to get that particular kind of thing wrong. So, why would we use this? Because it's quantitative, we can actually use it. I don't know tools that exist for it off the top of my head, but you could actually use it for tooling. Like you could add it to your pipelines to say, let's make sure we have no functions that have a cyclomatic complexity of over 8. And it will actually go and look through your code, and the pipeline might fail if you have code with too high a cyclomatic complexity. Generally, if your code has a cyclomatic complexity that's too high, it means you should break it up into other functions. The drawbacks of cyclomatic complexity analysis are that it assumes that your non-branching statements have no complexity, which isn't good. So it kind of assumes that if you have a function that's like 100 lines long with no ifs or whiles, that it's a really easy function, which is not always true. And sometimes code is best not to split up. Sometimes code can actually become more complicated if you break it up into more functions because it's harder to read. So, you know, it's not always something you should treat perfectly. Yeah, I've said that there's program stuff that does it. There's some further reading on the topic if you'd like. And that's it. If you could leave some feedback for this lecture, that would be exceptional. Would really appreciate it. And that's all we have today for cyclomatic complexity.